In this video, we're going to talk about the rates of chemical reactions and the things that can speed them up or slow them down. There are four issues that will increase the rate of a chemical reaction: the temperature, a catalyst, the surface area, and the concentration. These are all directly related to the rate of the reaction. So in other words, if we increase the amount of these, we will get a faster chemical reaction. So if you increase the temperature, the catalyst, if you increase the surface area, or if you add more to increase the concentration, you will get a faster chemical reaction. These are all based off of the concept of collision theory. What collision theory says is that in order for two particles to collide, or two particles to react, they need to collide with enough energy. We say the word sufficient energy because that includes enough, and proper orientation. That means the right parts of the molecule that form the bond have to collide to cause what we call effective collision. So an effective collision is a collision that results in a chemical reaction. If neither of these two things is met, no reaction. So in other words, if two molecules want to react, the parts of the molecule that are going to form the bond have to collide with each other. That's proper orientation. And they have to collide with sufficient energy. We would call this the activation energy from our last video. So they need enough energy to react. Be careful about the language here. Saying sufficient means you have enough. Saying high energy doesn't necessarily mean you have enough. That would be like saying I have a lot of money, but that doesn't mean you have enough money to buy, let's say, a sports team. So the idea is high and sufficient mean two different things. High just means a lot, but it doesn't mean you have enough to do what you are trying to do. Sufficient means you have enough to do what you're trying to do. So that is collision theory. So there are two very important things. If you don't have either one of these two things, no chemical reaction will occur. So the things that will increase a chemical reaction, the last thing we have to look at is entropy, or entropy is known as disorder in chemistry. So what we say is all things in nature tends towards maximum disorder. So things in nature actually they have two tendencies. They go to high entropy and low energy. So things in nature like to be lazy and messy. That's basically high energy and low entropy, or high entropy and low energy. Think of it like your room. If your room looks like this after you spent all day cleaning it, and then you live in it, but you don't actually clean it for weeks on end, eventually over time it's going to look like this. So this is high entropy. This would be low entropy. Low entropy means super organized. High entropy means complete chaos and unorganization. This would be low energy. This would be high energy. In other words, if you want to maintain this type of room, you are going to have to put energy into it in the form of cleaning it. That costs energy. This is what you get if you don't put energy into organizing it. You get low energy, high entropy room. All right, so entropy will play a role in this. Now, the things that will increase a chemical reaction, I mentioned them earlier, but we're going to look at why they work each time. So if you increase the temperature of molecules, they are going to move faster. That's because temperature is average kinetic energy, which is really just how fast the molecules are moving. So think of it this way. If the molecules are moving faster, they will collide more frequently and at higher speeds. So back to collision theory, they'll be more likely to have enough energy, and since there are more collisions, more of them will have proper orientation. That will cause the rate of the reaction to go up. It also means if the molecules are moving faster, they are going to be less ordered and therefore have higher entropy. So these things do affect both the rate of the reaction and the entropy of the reaction. Let's go to the next page. Concentration. If I increase the number of particles, well, that's just more disorder. Think about it. If you have a bookshelf and you only have one book, then organizing that book is very easy. It's just put the book on the shelf and it's organized, right? If you have a library full of books, well, then they are going to be much harder to keep organized. So the more particles you have, the more entropy you have, okay? Because there's more things that can be out of place. This also will affect the rate of a chemical reaction because more particles means you have a greater frequency of collisions, and therefore more of them will meet the criteria to cause a reaction. Surface area. So this is like if I take a sugar cube and grind it up into a fine powder. So because the powder can go everywhere, it can now be much more disorganized, so it will increase the entropy. If I just have one sugar cube, it's only one thing to misplace. If I grind it up into a fine powder, I'm going to have, hundreds of millions of tiny little particles that now have to be accounted for. So that's how increasing surface area will increase the entropy. It will also increase the rate of a reaction for the same reason the concentration does. If the particles are more spread out, then they are more likely to come in contact and collide with the other chemical that they need to react with. It's like having, think of it like the expressway and car accidents. The more cars that are on the road, the more likely there's going to be a collision. All right. And also, the faster you let the cars move, the faster the speed limit, the more likely you are to have a collision. And so that's what this is really talking about. If there was only one car on the road and it was parked, well, it's never going to get into an accident. The moment it starts to move, it could start hitting things. And the moment you start adding more cars on the road, the frequency of collisions will increase. If you want to increase surface area to its maximum, the way of doing that is dissolving it in water. Because if you think about it, if I take a sugar cube and grind it up into the finest powder I possibly can, right? Those tiny little particles that can almost float, they're so fine, almost like dust in the air, they are still made up of millions of sugar molecules. So the way you make the sugar molecule spread out the absolute most is by dissolving it in water, and the water molecules will actually take the sugar molecules and individually spread them out. That is the maximum surface area you can get. No amount of grinding something up will even come close to being able to have that amount of surface area. And then last, spontaneous versus non-spontaneous. So chemical reactions there are two types. There are reactions that are spontaneous, and then there are reactions that are non-spontaneous. A spontaneous reaction, think of the word, it's nothing complicated. It's literally an English word. It means something that kind of happens without planning. So if you trip, that was spontaneous. If you plan a trip, like a different type of trip, like a vacation, right, that's not spontaneous. You plan that ahead of time. So spontaneous reactions occur on contact, basically without any outside help. The example, Alka-Seltzer and water. If I take an Alka-Seltzer tablet and I put it in water, it starts to fizz the moment they touch. That is a chemical reaction, and that's happening spontaneously because all I had to do was let the two things come in contact with each other. So reactions that tend towards high entropy, they tend to be spontaneous. Not all the time, but this is just a generalization. Now, non-spontaneous reactions require some outside help, typically heat, but not always, like lighting a match. In other words, if I take the match tip and I put it on the striker pad, the moment they touch, well, nothing happens. In order to make the match light, I need to rub the match head along the striker pad in order to get enough heat in order to make it react. That is an activation energy. We've mentioned that before, but it's also a non-spontaneous reaction. They won't happen on their own. Okay, so reactions that become more organized over time in general favor lower entropy. They tend to be non-spontaneous. I'm not too worried about those last two. Those are more, there is a way of proving it. There's actually a mathematical formula for figuring out if the reactions will be spontaneous or not, but we are not going to learn it. So that includes our lesson on rates of reaction and spontaneous and non-spontaneous reactions.